So something that you guys mentioned in the exam wrapper is that you wanted to see some more problems. So I'm just going to run through these ones really quickly. I'm not going to plug in the numbers, but I'm going to set them up algebraically so you can see what you're doing here. So the first question says you're going to have this cylindrical turntable that has a certain radius. I'm going to call this some radius of r. And it has some known mass. And it's rotating with some angular velocity that is also known. We're going to call this an angle. This is an angular velocity of omega. And we're going to drop some lump of clay to this. And this lump of clay is going to stick to it. And it's going to be at some distance. So I'm going to draw this distance that this is. It's kind of like projected upwards so that there's like some vertical axis here. And I'm dropping that so that when it lands, it's going to be a different distance away from the center. It's not going to be the whole radius r. So the first thing we want to do is we want to find the angular speed of the clay in the turntable after this sticks. So classic angular momentum, conservation of angular momentum kind of problem. So what we want to do is we want to sum the angular momentum in the initial state. This is going to be equal to the sum of the angular momentum in the final state. And we know that the angular momentum of a rigid body is going to be equal to I times omega. So this is the moment of inertia. And this is the angular velocity. So in the initial state, this lump of clay is not going to be creating any angular momentum itself. It doesn't have any angular momentum in this system here. So the initial angular momentum is only from the turntable. So we have some I, let's call this an omega naught to denote that it's the angular momentum in the initial state. And then in the final state, these two things are going to be moving together. And so this turntable is going to have a new angular momentum. We're going to call this omega 1. And the mass is going to stick here. So in the second state, this mass is stuck now to this. And then this is going to be rotating with this angular velocity, omega 1. Okay. So when we have a point particle, we can consider the moment of inertia of it about the point of rotation to be mr squared. Okay. So this is going to be plus m of the putty that you're dropping times r squared, where its r is going to be the lowercase r. So here's our mass of m. And so this is going to be multiplied by the same omega here, right? Because they're rotating together. So this is effectively what I did right here was this is writing in the moment of inertia of the point particle. So now, the next thing that we want to do is we want to find what the angular velocity omega 1 is. Well, we can factor that out from each of these terms and then rearrange this. And this is going to say then that omega 0 is, sorry, we're solving for omega 1. Omega 1 is going to be equal to I omega 0 divided by mr squared plus I, where I, the moment of inertia of the disk, is going to be equal to capital M times r squared. Okay. Now, the next thing that we're asked here is the mechanical energy of the turntable constant in this process. And it shouldn't be, right? Because the energy is not going to be conserved in this case. There needs to be some non-conservative force to get this to stick here. And so if what we did was we calculate what the initial kinetic energy is, this is just going to be 1/2 I omega naught squared, and then the final kinetic energy. So this kinetic energy final is going to be equal to 1/2 I plus mr squared, or lowercase mr squared. This is, sorry, this moment of inertia is, there's a half here that I left out. I need to be really careful. I'm very tired, so I'm hopefully not going to make too many mistakes. So this is going to be plus m lowercase r squared, okay, times omega 1 squared. Okay. Now, if I calculate this with the values that they gave us here, what we would end up finding is that Ki is greater than Kf. So it loses kinetic energy in this process. So let's call this part A. Let's call this part B. Okay. And for part C, is momentum of the system constant in this process? Well, the question should kind of specify what's meant by momentum. I'm going to assume here that they mean linear momentum, because we had to use a conservation of angular momentum. So P vector is not conserved. And the reason why P vector is not conserved is because if something has some momentum in this direction, let's draw like a little circle that this can go around, and then it has some momentum in this direction, the direction of the momentum changed. So that there needs to be some force associated with this in order for the momentum to change. And if there's some force, that means that the momentum is not conserved. Okay, so let's move on to the next one. The next one, this is a conical pendulum. So it says during the motion, the supporting wire length L maintains a constant angle of theta. Show that the magnitude of the angular momentum of the bob about the vertical dashed line is given by this thing that they have here. Okay, so this kind of goes back to sum of forces in some ways, because what we need to find what the velocity of this is going to be. Because in order to find the angular momentum, we know that L is going to be equal to R cross P, okay? Which in this case, this is going to be mag R, mag P, times the sine of the angle between them. So when we're looking at this, and let's look at it top down, in the plane of motion, so I'm looking like straight down here, in the plane of motion, this is R, okay? Now, projecting this back the way that they have it here and drawing this here, here is R. Right, let me do this in a different color so it shows up a little bit better. So here is R. I don't know if that's really any better. So here is R. None of these colors work very well. So how about white? There you go. There's white. White's going to work. So this is how I'm defining R right here. And this R is going to be equal to L times sine of theta, okay? So that's R taken care of, but we need P, and that's ultimately why I said we're going to have to come to using some of the stuff that we use for circular motion, because P is going to be equal to mv, right? And the sine of theta, this is why I defined it like this. This is going to be 1, because these are perpendicular to each other. So P is equal to mv, and so we need to determine what this tangential velocity is. So in order to do that, we have to draw a free body diagram. So we have our tension here, we have mg, and then we need to sum our forces in x and sum our forces in y. So summing our forces in x, is x and y, says that this is going to be equal to minus t times sine of theta, which is going to be equal to ma, but because we're dealing with circular motion, this is going to be minus mv squared divided by r, same r that we had there before. I'm just going to carry it around as an r for right now. So for our sum of forces in the y direction, we're going to get t times cosine of theta minus mg is going to be equal to 0. So now what we can do in order to get this so that we can get rid of t, because ultimately we need v, right? Ultimately we need v here. I'm just going to take the top equation and divide it by the bottom equation. And so when I do that, our t's are going to cancel. This ratio of sine over cosine, this is going to be a minus tangent of theta, is going to be equal to minus mv squared over r. We have an mg here, this would move over to the other side. So I'm moving this over to the other side when I'm doing this implicitly. So we have a minus mg, and that becomes plus on this side. So at the end of the day, what we have is this is going to cancel. This is going to be a v squared. This is a g, and then this is going to be positive. I got rid of my signs. Okay. So the whole reason why we did this is because we need to know what v is. So v is going to be equal to the square root of gr tan of theta. So now that we have this guy, what we need to do is we need to take him and use him in conjunction with, excuse me, use him in conjunction with what we found up here. So we want to calculate the angular momentum. L is going to be equal to R times P, which is going to be mv, and then this is going to be R times m times the square root of gr tangent of theta. So now what we can do is we can plug in what we have for this right here. And so when we do that, we end up having, this is going to be L sine of theta times m times the square root of g times L sine of theta times, this is times theta, sine of theta times tangent of theta. Sorry, I'm a little scattered right now, guys. I'm really tired. So this is going to be tangent of theta. So what we can do with this to get this in the form that they have here is we can bring this on the inside of the square root. Okay, they leave the m on the inside? No, they bring the m on the inside too. So really, one way to write this would be L sine of theta times m to the 2 over 2, okay? Because implicitly, these are all raised to the 1 power, and 2 divided by 2 is 1. And then the square root really is raising to the half power, GL sine theta tan theta, okay? So this is like, it's a 1/2 power. So we can bring this on the inside here if we move this. It's kind of like factoring the denominator out in some sense. So what I'm going to do is I'm going to do this as mlg sine theta quantity squared times gl sine theta tan theta to the 1/2. Okay. And then the last thing that we can do here is kind of distribute everything, and they have this in terms of a cosine. So this is going to go back to being a sine divided by a cosine. We're going to have 4 factors of sine. So let's collect all of our terms so we have the final answer here. So L is going to be equal to, this is going to be equal to m squared L cubed G cubed times sine to the 4th of theta divided by cosine of theta. And hopefully I didn't make any mistakes with bringing everything in there. So we, they have a G, not a G here. So what happened to my G's? Oh, I invented a G. I invented a G. You see how I wrote a G there? That was careless. So that should just be like that, and then that should be the answer that they have there. Yeah. Sorry, like I said, I'm trying to get through these pretty quickly so I can go home. So m squared G L cubed sine to the 4th. G. Yeah. Okay. So this is the same thing they had here. Okay. So personally, I really like these kinds of problems. Because they give you what the answer is, and then your job is to prove why it's the answer. I think we should do some more of those. So the next problem, this one kind of connects the kinematics that we had done previously, and then the torque and angular momentum come into play as well. And so the same thing with the one after that. So here they tell you the velocity, v vector, is going to be equal to 6t squared. I'm going to call these x hats and y hats because I like that notation better personally. But you can choose whatever notation you're comfortable with. As long as you're representing your ideas correctly, it doesn't matter what the notation is. So what we're going to need several things. And I'm just going to do a whole bunch of calculations here, and in the end, I'm going to have everything that they have. To find the acceleration, we're just going to take a time derivative of this. This says this is going to be 12t x hat plus 2y hat. Finding what the position vector is going to be integrating this. So when we integrate this, we're going to get a t cubed divided by 3. That's going to give us a 2t squared. Integrating this one raises this to the second power divided by 2, gives me just t. I'm missing my cube. So this is cubed, and then this is just going to be t squared. And I lost my x hat and my y hat. So now that we have these 3 things, what we can do is we can calculate our torque and our angular momentum. So torque is going to be equal to r cross F, and L is going to be equal to r cross P. Okay. Now this can be rewritten as, because F is going to be equal to MA, and P is equal to MV. So this one right here can be rewritten as MR cross V, and this one can be written, I'm making mistakes again. This can be rewritten as cross A, and then this L can be rewritten as R cross V. So let's start with calculating the torque first. So this is going to be M times our R, which is going to be 6t cubed x hat plus t squared y hat, crossed with the acceleration, which is 12t x hat plus 2y hat. Okay. So we could FOIL this out, or we can remember this formula that I showed you in one of the previous videos that said that this is just going to be M times Rx Fy minus Ry Fx. You could do either one. I'm going to go for the foiling here. So what I end up having is any terms where x is multiplying by x is going to be 0. Any term where y is multiplying y is going to be 0. So the only 2 terms I have are the cross terms. So this is going to be 2t cubed x hat crossed with 2y hat. And then the other term I'm going to have is going to be, this is going to be plus t squared y hat cross 12 t x hat. X hat cross y hat we saw was going to be z hat. Y hat cross x hat is going to be minus z hat. Okay, and so what we see then is this term right here is going to end up being 4t cubed times z hat, and then this one right here is going to be minus 12t cubed z hat. So we end up having this is going to be minus 8t cubed z hat. Okay. Now, the next thing that we can calculate is the angular momentum of this, and I'm going to just calculate this using essentially the same process. And I'm going to copy this guy right here, and I didn't get the whole thing. I'm going to copy this guy here and move him down so I have room to see this, because I need all this information. So I'm going to paste you there and then move you over here. You're going to work with me. Come on, man. You're going to work with me. Of course, it like pastes it in a really stupid place, which is all the computer really knows how to do, is do what you tell it to do. So now I'm going to calculate the angular momentum here, and it's essentially the same thing that we had here. So this is going to be L vector is going to be equal to R cross P, which is going to be equal to Rx. I had this in a mass before, so this is going to be Rx times Vy minus Ry Vx. And now let's just read off the terms this time instead of foiling it. It'll be the same thing. So this is going to be Rx, which is going to be 2t cubed, times Vy, which is going to be 2t, minus Ry, which is t squared, minus t squared times Vx, which is going to be 6t squared. 6t squared, yeah. So this ends up being m. I lost an m with this calculation here, so this whole thing needs to be multiplied by an m. So, and again, I talk about this a lot. You want to be thinking about your calculations and kind of going back through them, because I realized that I lost an m there because I'm going to go somewhere in particular with this to prove that these two are the same thing. And I need the m in order for that to happen. So when I multiply this together, I end up having, this is going to be 4t to the fourth minus 6t to the fourth. This is going to be equal to m times negative 2t to the fourth. So here's our L, okay? And in principle, we had this in the z hat direction. Z hat, z hat, z hat, L vector. Now, we know, because we've proven it when we used this before, that the torque is going to be equal to dl dt. So I can take a time derivative of this, and when I do that, I end up finding this is going to be 8mt to the fourth z hat. But if I look at this, this is exactly the same thing that I had when I did this calculation here, if I knew how to take derivatives. So when I took this derivative, this should have been a 3. But again, you know, because these need to be consistent with each other, I made a mistake somewhere, and I could spot it because I did this multiple ways. It's always a very good way to check yourself, to do the problems multiple ways, if you have the time. That might not be the best way to go about an exam question, but as you're learning and you're doing more complicated problems, it's always good to try to do your problems multiple ways, because you end up finding that if one way is wrong, then if your answers don't agree, then either both ways you went about it are wrong or one of the ways is wrong, but they should be equivalent to each other. It's probably one of the best ways to check your work is to work a problem multiple ways. Okay, so the last one that we have here follows in a kind of similar fashion to the last one, and in that we're going to be calculating the torque and angular momentum for this object, because we can figure out what its position, velocity, and acceleration vectors are. So this is just a projectile, the same way that we had done them before. So what we're going to have here is r vector, and I'm just going to write this out because we found this before. R vector is going to be equal to v0t times cosine of theta times x hat plus v0t sine of theta times minus 1/2 gt squared times y hat. V vector is going to be equal to v0 cosine of theta x hat plus v0 sine of theta minus g times t times y hat. And then a vector is going to be equal to 0 x hat minus g y hat. So we want to calculate the torque and angular momentum in this case. So we say that the torque, I'm sorry, I know I'm going really quickly, but I want to get this one out and done. So the torque is going to be equal to r cross f. This is going to be rx fy minus ry fx times z hat. And so we can read this off term by term, remembering that the force is equal to mass times the acceleration. There is no force in the x direction, which makes this term right here 0, right? Because the force is only, there's no acceleration in the x direction, there's no force in the x direction. So then we end up having, this is v0t cosine of theta times minus g, okay? Or this is going to be minus g v0t cosine of theta. That's our torque. Now we want to find our angular momentum. Angular momentum is a little bit more complicated because we're not going to get 0 for this, for one of the terms. So this is going to be R cross V, which is going to be equal to Rx Vy minus Ry Vx. And we have a mass out front. Don't forget our masses, very important. I left off a mass here. Left off a mass there, and there. Yeah, when I went from this line to this line, I was using sum forces equal mass times acceleration. I left off the mass. So there's a mass there, and then there's a mass on the outside of here. And then this is times the z hat. I lost my z hat too. And then this is times the z hat. So this we can read off from here kind of the same way we did the last one. This is going to be v0t cosine of theta times v0 sine of theta minus gt, and then mass times this whole thing, minus ry, which is going to be v0t sine of theta minus 1/2 gt squared times vx. So this is going to be a v0 cosine of theta. Well, this is an interesting calculation because I'm just going to pause here and say why I think this is an interesting calculation. So you end up, when you do a lot of these problems, you start to see patterns and you start to notice how things are going to have to work out in order for you to get the answer that you're expecting to get. So when I'm looking at this, you see how I only have a cosine of theta, but this has sines of theta in here, which means that somehow they're going to have to cancel. And so that's why I say the problem's interesting, and we're going to see why they're going to cancel in a second. Now we just need to expand this term by term. And you don't even necessarily need to do that. You can look at it. You can look at it and say, this term times this term is the same as this term times this term, but then this one has a negative sign, right? So what that means is that those are going to cancel each other, okay? And so what we're left with then, this is going to be m, now let's expand it. This is going to be v0 t minus g cosine of theta minus 1/2 minus 1/2, so that becomes a plus 1/2. I lost a 2 here, so this is t times t, it's t squared. 1/2 g t squared times v0 cosine of theta. Now sometimes you get to this point, you have to look at this to see that these actually are the same, because I didn't write the variables in the same order. So v0 g t squared, v0 g t squared, cosine, cosine. I can add these to each other. So, or what I could do is I could factor the whole thing out. So if I factor the whole thing out, this is going to be minus 1 plus 1/2 plus 1/2. Shit. What happened? No. What are you doing to me, man? Okay. We gotta go, and I don't want to edit this one. So, okay. So, we'll do it live. We'll do it live. Oh boy. Oh boy. Okay. We got it back. Maybe we have it back? We do not have it back. Okay. Keyboard to the rescue, please. No. No. We were doing so well. Why would you do this to me? Why would you do this? Okay, no, it's back. It's back. Okay, okay. Yes, yes, I have touch control. Okay, I'm way too lazy to edit another video 2:30 in the morning. So I lost that last line. That's fine. So what we had was these two terms can be added together, or you could factor out this v0 gt squared cosine of theta from each one. So this is going to be m times minus 1 plus 1/2 times v0 times g times t squared times cosine of theta times z hat. And then 1/2, negative 1/2. 1/2 minus 1 is negative 1/2. And so what we have is this is going to be minus 1/2 mv0 gt squared cosine of theta times z hat. And that is our angular momentum. And so the very last thing we want to do is we want to check this the same way that we checked the last one. So the way that we checked the last one was we took the time derivative of our angular momentum. So let's take a time derivative of this, because we know that the torque, tau, is going to be equal to r cross f, which is the same thing as dl dt. And so we do dl dt minus 1/2 g m v0 t squared cos theta. For reasons unknown, I'm rewriting these in different orders. But if you do this time derivative of this t squared, because everything else is a constant, this ends up being equal to minus, let's put it back in the right order, mv0 g cosine of theta times t. Okay, and if you look at that, hopefully I didn't make any mistakes, because I went very, very quickly through there. I did lose my z hat, but this is the same thing as this. Okay, so that's going to be it for me tonight, guys. I'm going to go home and go to bed, but I hope that helps you in studying. You've seen kind of more ways that you can use these problems. And I know I went through this very quickly, so if you have questions about what I did for any of these, just let me know in Teams, and I'm more than happy to help you. Okay, so take it easy, and I'm going to go to bed.